pleasure to me. I don't find the time, but okay, finally. And okay, let's see this way. Okay, it goes better. But okay, you still hear me? Okay, because I have a strange feeling I don't understand what changed. Okay, and so I hope to get you interested as maybe my approach is a little bit different from your usual way, with some idea about integrability, despite the title. And we will see how we would approach system that may be more interesting for you. Keep in mind, please, since the beginning, that actually, usually people talk about integrability about some, how to say, some solvable system, this kind of words. Okay, this is, so be very suspicious when someone introduce for you integrability in this way, because it's a different story for experts really working on integrability, because integrability itself, it's a concept you will see that is moving, I'm referring to quantum integrability, moving, deforming in such a way to explain physical and mathematical phenomena, say this way. We will see how this take form quite concretely. And, but it takes a little bit to reach this point. And already in the title, so I want to get to gauge theories, which is something that maybe I hope very interesting to you. And but anyhow, there is also something very little for the time being we can say about black holes, and especially about what are called quasi-normal modes in black holes. But also love numbers. So things, love is not a word, is the name of astronomer. A concept very much tied to an interesting for gravitational waves and gravitational physics. And basically, I'll be telling you things that are results containing several works, published or not with these people and maybe other people. Okay. Usually, for people working, say, on integrability between inverted commas, because as I said, especially for the STFT, you should have learned that integrability was a very changing object, which is still a little bit undefined. But anyhow, trying integrability means basically, so whatever happens after Liouville theorem, and due to the fact that we don't have any Liouville theorem, this is the problem, but also the advantage, okay? So there are basically two big motivations moving us. One is internal, inside, say, the integrable community. So the idea is to understand this, the most general integrable theories. As I said, actually, we should say a little bit also with some epistemology to understand what quantum integrability could be, in such a way to have exact or non-perturbative results, okay? So to devise methods to have this kind of results. And this is due to the fact that, as I already anticipated, the integrability doesn't mean that the system is solved. Actually, on the contrary, you know something, you can write maybe some equation up to quadratures, okay? We will see what it may mean in some cases, okay? But there is still much work to do. And this is quite a general problem on quantum field theory, for instance, but also in other fields, also in quantum mechanics, because we usually have also in particle physics at LHC, we have asymptotic series. For the standard model, we do have asymptotic series. We don't have convergent series. And we have to care for the resummations. And then we have integrability is rather familiar with the spectrum, but it's still a very long ongoing path. The possibility to reach off-shell quantities like correlation functions. For instance, also correlation functions. You can think, for instance, of correlation functions for the prototypic, very famous theory, quantum Saint-Gordon theory, okay? And what do you know about correlation functions in quantum Saint-Gordon in 2 dimensions? I mean, perturbatively, okay, using Feynman diagrams again, you can do something like this. But what about exact objects? On the contrary, just a flash. If you think of conformal field theory, okay, you have a very famous to you now because of, for instance, AGT conjecture. You have the BPZ equations, so word identities, plus null vector. And then you can write quite concrete correlation functions for conformal theories. But once you very simply, also from a physical point, from a physical point of view, you add the mass to a conformal field theory, you perturb the conformal field theory, say a la Zamolodchikov, at least ideally, but you can do this concretely. And then you for instance, Saint-Gordon is already a perturbation of C=1 theory. Then Virasoro is destroyed. Everything you have done is destroyed, fully destroyed. Okay, the 2 theories no longer conformal, and then you have you enter a lot of troubles. You may think that maybe the more expert among you may think of 4 factors approach, but that's a full different story, and is not a complete description under many perspectives. We may discuss about it if you're interested, but it will be a long story. Probably what we are more interested in will be the external reason which lead us, okay? And the fact that using the 2-dimensional world, we can somehow holographically, in different meanings, project us towards higher dimensional theories. For instance, ADS-CFT dualities, n=4, which is the prototype. But also, we will see something many of you know even better than me about n=2 supersymmetric gauge theories. And more recently, there are some clues about gravitational physics. Of course, also quantum entanglement, information transport. So people now are using spin chain, integral spin chain for doing almost, or testing almost everything, as you well know. Things that have been abandoned somehow for a long, Here, a concrete example, if you have your, the 2-dimensional, the flows of the 2-dimensional theories, this is a little bit how it works. You can imagine, as already anticipated, that you start from a UV point and you perturb your theory, your conformal field theory, using a massive flow. Very recently, you have seen that there has been a very quite a success of investigation of massless flows like TT bar. You for sure know about this. And in this way, using the finite size spectrum, you can span the space of the 2-dimensional theories, okay? And this idea is equipped with some exact methods, at least for what concerns size spectrum. We will see in a moment, to have control in a non-perturbative way, in an exact way, of what is going on in these different possible paths. Okay. And start to describe the approach, some usual approach to quantum integrability. Very simple, but very different from what you can imagine. And then let's see how this glues to maybe theory. in one time and one space dimension, okay? You may think of quantum field theory, but also here probably quantum field theory is more familiar, but also of a spin chain. And we have particle scattering, okay? Also in spin chain you will have some things, because in the end, in spin chain you will have spin waves or representations for those of you who are more mathematical oriented. And there is quite developed mathematical theory about this, all this. And very roughly, we can start with a definition of integrable, just saying that we have an infinite number of conserved charges, okay? And we don't say very much about this. These models are not trivial and not solved, but and there are many, basically because you don't know so easily what to do with these charges. Very often these charges are abelian, so they are in involution, which doesn't help you very much. As said, we will try to specify somehow this notion of integrability, changing it a little bit, making it more specific. You will see. Let's go to the whole theory. So the statement of integrability. You have a two-body scattering, okay? And since you have an infinite charges, you can very easily imagine that the scattering of two particles of different masses. No, I don't know why. Okay, there are too many pointers. And not so much changes in the scattering, because everything has to, these charges have to be conserved. So in particular, the momentum and the energy of a single particle. But what happens in this, is the scattering is that you have a sort of delay, a phase shift, when the particle after the particle scatter. So they outcome with the same masses, but with a phase shift, okay? Something more interesting may happen if the masses the masses are the same. In this case, there is some mixing, there is some change of the internal degrees of freedom. For instance, color or flavor. For the very well-known example is the soliton anti-soliton for the quantum Saint-Gordon theory. Then you may have two kinds of channels. One is scattering, one is soliton anti-soliton into soliton anti-soliton with the phase shift, but the other one is the reflection. So you have these two possible channels of scattering. And in this way, the scattering is said to be non-diagonal, because you don't have the emergence of. More interesting is the situation for a three-particle state, but again, due to the infinite number of charges, you have this property in which the order doesn't matter. So first, you can imagine you have the scattering of green with, I think this is black, and then black with yellow, and then yellow with black, but it's the same if you move this black all to the right. This is a sort of, also if you famous relation which goes under the name of Yang-Baxter relation. Once you fix this, basically you have that the n-body scattering is fixed because it can be factorized into two-body processes, because the order doesn't matter. This is the idea. And also general theory later than this developments in physics, but say that general theory of quantum groups formalize this kind of stuff. Let's make an example. We may start with relativistic theories to make things simpler. People working at the SCFT, but there are not so many here, will be unhappy about that because in this case, the rapidity which matters is just the difference of the two rapidities because of relativistic invariance. And we may start with Sine-Gordon, okay, quantum field theory, which has this a very simple, apparently looking Euclidean action. The problem, we will go with this theory is that it's already a little bit involved, and the scattering is non-diagonal. So mathematics is quite complicated. It's a little bit complicated to deal with all these channels because it's non-diagonal, and it can be done. Keep in mind that this theory, you will see, it's somehow the parent theory of what we are going to discuss about. Sort of more complicated theory from which you can derive the child theory. The child theory is this simple relative of Sine-Gordon, which is hyperbolic Sine-Gordon, okay? You can roughly do a sort of substitution of the coupling constant, making the coupling constant purely imaginary. This is not an analytic continuation at all. People talk about analytic continuation, but you can imagine the spectrum changes abruptly. So since here I imagine to have a quite sophisticated mathematical audience in front of me, imagine what is the analytic continuation if this object has, as you well know, soliton, anti-soliton, and breeders. This object here has only one particle. Morally, this particle will be, okay, people say that will be the lightest breeder of the Sine-Gordon, everything else is truncated. But this is something for people who know very well mathematics and even better physics, okay, because it's a very delicate process. This theory is really very different. In my perspective, you will see in which sense it involves integrability. This is a child theory. There are also people very expert about this. So this is somehow a sort of generalization of the Painlevé gauge correspondence, okay? It's, Painlevé is 1 plus 0 dimensional. Here, everything is 1 plus 1 dimensional. You will see also in which sense I get from this the Painlevé equation as a subcase, okay? And this is the child theory. So for simplicity reason, for pedagogical reason, we will discuss about hyperbolic Sine-Gordon. Everything can be said, playing a little bit with indices, for quantum Sine-Gordon. We will assume at the end. Sorry, Sine-Gordon? You will see in a moment basically we are interested to get really the gauge theory. We have something more complicated. We don't know what it is from the point of view of gauge theory. That will be an interesting question. But in a particular limit, you will see in the end, and we may also discuss about it, we have something more general, okay? But also the gauge side we will get is not, I anticipate to you, since I know what you are heading to, the gauge we will get is not the gauge in the Painlevé gauge correspondence by Lissovi and collaborators, because in that case you have the self-dual regime of omega backgrounds. We will instead land on Nekrasov-Shadashvili regime. Absolutely, yes, but also related by other relations due to integrability, which are a very simple manifestation than the blow-up equations. Because blow-up equations are quite complicated also for experts. And I remember so very long chat with Bonelli who was trying to understand. Okay, be patient because otherwise, you know, the point is that we are taking off from a fully different perspective from usual what people would refer to as quantum integrable theories. because everybody talks about integrability, quantum integrability, but this is the old path, the old things due to Zamological, where all of us were in the, if born in the school, okay? Otherwise, quantum integrability are just words, okay? And this is very connected to the original paper by Baxter. It's real integrability, otherwise. Okay, so this is our simple object. Only one particle. This particle scattered with itself, and this is the two-body matrix. This is why I choose. Also because, as I said, the geometrical structure, it captures somehow the geometrical something of the parent theory. But anyhow, the coupling constant is in this object here, in this variable here. Beta is the is the original B in the Lagrangian. Then you construct Q, and then from Q, P. So basically, P is a simple, very simple rational function of B. Unknown shell information, as you understand, it's a scattering amplitude in infinite sites. The first problem is for integrability. The first problem was actually solved not so many years ago. At the end of the day, was what can we say about the finite size energy, something which is already off shell, okay, using this on shell information. Okay, here the idea is to use Bethe ansatz. The physics of the Bethe ansatz is very simple. You know it very well. You have you consider the propagation of a test particle, which is the blue one here, and it scatters with all the others, the green ones, and then come back. When it does this, the phase of the wave function goes back to 1, okay, and you have a propagation, free propagation of it, and a certain number, say L minus 1 scatterings with the other particles. This is the process. And this is a different scattering matrix, the original one due to Bethe, okay, for the XXX spin chain. I'm unifying a little bit now in this language, in this mathematics, field theories and spin chains, okay? Why? Are exact for spin chains, okay? You can diagonalize very simply XXX, and from there you can diagonalize Hubbard, whatever you wish, XSZ, so it's technically more complicated, but basically the idea is over there. Also Mathematica, you can use more sophisticated ways, which have also other, this is called the technically coordinate Bethe ansatz. You can use other ways, exploiting quantum groups in the end, like algebraic Bethe ansatz, so on and so forth. But the okay. The real problem here is physically is that, okay, you imposed periodicity of the spin chain and the phase. It's true for spin chain. For field theory, since S is an information in which the size is infinite, so this equation are not true for finite size of my cylinder, of my space. Totally. In this way, I can get approximate informations. Sometimes these information are called Bethe-Young equation, which are asymptotic. Asymptotic, this is very well known in integrability applied to the SCFT. Numbers of your theories are very large. Somehow the length of your spin chain, which is not a real spin chain because it's a quantum field theory, is of infinite length. Point is, how can I get now exact information from this picture in a physical way? The idea is the following. You try to compute the partition function, say, on a torus or an infinite cylinder, infinite because you can imagine that the time R is very, very, very long, at least compared with the space L. The space L was the space, the finite space on which we were working on, okay? And when L is very, very large, this equation becomes exact. Unfortunately, we want L to be finite, and this means that this is not an equation, is an approximation, okay? It will be an equation for spin chains. But since we are interested to quantum physics, it's an approximation, okay? And we are stopped. I'm repeating what I said before. But now the novelty is that I put inside this simple geometry, you can imagine this. People may be interested in string theory, and I use somehow a very simple concept in string theory or conformal field theory. So I have a direct theory, which is my starting point. In this direct theory, the partition function of my theory can be computed, and the leading object for I'm looking at the ground state energy of the particles moving here. This delta zero, I call it delta zero because it's really a conformal weight of n equal 4, for instance, in the SCFT. Also in lower dimension. This is nothing but the ground state energy, okay? The problem stays still there. But now I make something physical, which is nothing at the end of the day that modular invariance. Somehow in statistical mechanics this is called also Matsubara transformation. Call it as you wish. But I simply, instead of looking at the theory as space and time, I'm inverted too. Or if you wish, instead of looking at the theory from here, I look on the other channel. Now this is the space, and this is the time. Now the space is very, very large. So I'm authorized, I may use my Bethe ansatz equation in an exact way, because R for me is infinite. I said at the beginning, this is not really a torus. I use the term torus to make contact with modular invariance in string theory, for instance. It works also for non-conformal theories, okay? The worksheet can formal, because the physics is simply that I'm computing the same object, but on the other channel, okay? And this torus is very long, okay? Actually, is a cylinder. There is also, for people who know open string theory since the old time, it was introduced basically by Sagnotti and collaborators, the annulus duality, which is exactly this. But anyhow, the mechanism physics is very simple. So now the point is that I don't, strictly speaking, since I imagine you are very attentive, I don't have the scattering matrix of this theory with this space. I do have it for this space, but this is not difficult mathematically because this is a genuine analytic continuation in theta, okay? Basically, it's a translation of I pi over 2. It was more complicated when we did this for our crucial result in the SCFT spectrum, because there everything is non-relativistic, but in relativistic theories it's very simple, so you can derive the scattering matrix here, you are happy. The last problem is, okay, I'm left with a time which is compactified. And this is somehow the magic tool which enters the game. I can deal with this compactified time using an old idea by Yang and Yang, reformulated somehow with this variant by Alyosha Zamolodchikov. I consider this time L wrapped as the inverse of a temperature, okay? And I make some Bethe ansatz plus thermodynamics. This is why it's called thermodynamic Bethe ansatz. It's not exactly the original Yang thermodynamic Bethe ansatz, because I have this modular or Matsubara transformation, okay? Because people refer to modular transformation, the one used by Cardi, so in conformal field theory. Here we may be fully non-conformal. You already have, actually, for conformal theories, the concept of scattering matrix will be very, very delicate, okay? So we are massive since the beginning, somehow favorably. Let's go to some practical computation. When, again, R is, it's really an anomalous, this object here, but with periodic boundary conditions. The same partition function, Z is the same, there is no dual Z, it's the same, is given by this, the leading object, the leading term in large L, R, sorry, is given by this object here, where now F min is given by, is the free energy. Is the free energy, this scattering theory, and the free energy for, in temperature, say, or beta. Beta is L, the beta, beta of yesterday is L, okay? And is dominated by this object here. Of this object, contrary to what happened to this object here, this is the unknown, we can compute this free energy, okay, using thermodynamic Bethe ansatz idea. And we are left with this equality, in which this is the unknown, this is a very well-known object. Known because we can compute it, since actually thanks to Yang and Yang, okay? At least for the ground state. For the moment, we are working on the. This is why the ground state we were discussing, working here this morning. The ground state is particularly important and principal in integrable models. Okay. Out. Quantity, in particular free energy, so you can really compute it counting the particle, blah blah blah. I don't have time to do theories and so on. So linear functional, okay. As said, for relativistic models, this applies very easily because the mirror theory is the theory I see looking at as, from here as space. It's technically called mirror theory because you have exchanged space and time. DS are the same, okay? Because nothing changes in this analytic continuation. In general, it's analytic continuation because there is the difference of rapidities, okay? And as said, I have the minimizing the nonlinear functional leads me to nonlinear TBA equations. This is the origin of the TBA equations and of their nonlinearity, intrinsic nonlinearity, important nonlinearity. It's due to the thermodynamics. And their solution gives me the energy, okay, via this free energy, which is a nonlinear functional. You can do everything very simply for this specific theory, hyperbolic sine Gordon. This is also why I choose it. And this is the ground state energy. I'm confined at the ground state. You may ask about excited states, but it's a different chapter. As said, this energy is a functional of a pseudo energy, this quantity here, epsilon, and the epsilon is governed by this equation. This is a sort of dynamical equation in theta. Theta is the rapidity, the original rapidity, for this epsilon. You solve it, you solve this equation, so somehow this is the solution up to quadruples. Find epsilon, insert epsilon here, you get the state energy, which now depends crucially on the sites. We wanted exactly this. And for infinite sites R, you should recall the approximations, okay? Pay attention to the fact that the only ingredients of the scattering theory here, the theory we departed from, is this phase shift here, is this scattering, is the logarithmic derivative of the scattering matrix, okay? More complicated your theory as for the spectrum, more complicated this equation can be, okay? But let's go, one way to solve this equation numerically could be just to start from the driving term. These are called the driving term, this term which is here, and put the driving term here, and you make a calculation. You get a first approximation. You use this for a second approximation and so on. This is a recursive way, like the Neumann series, but this equation is non-linear. You see the log here is intrinsically non-linear, and we will see with very beautiful features. I'm afraid I have to rush a little bit. But yeah. This is, by the way, the infrared approximation of your theory. At infinite R, you can imagine that this object, the integral doesn't count so much. And this is the main object you deal with. So physically what you are doing very quickly, you understand that for a large R, thanks to this equation, this is a sort of equation of exact equation of the renormalization group, because from the infrared, large R brings you to the ultraviolet. And you can really compute. This is why this equation was initially devised by Alyosha Zamologin a long time ago. You can really compute the conformal field theory data, okay, from some infrared information only. So quite impressive from the point of view of physics. But now we are departing. I said that because this is the old story somehow. Very important. Or just because of time, chronologically. Because we need to depart from there to understand how to get to other approaches. You can write explicitly, okay? This is the kernel, okay? If you remember, you have two terms in the arithmetics, okay? And then from this equation, not the reverse, you define y in this way, basically minus the exponential of beautiful blackboard. I cannot resist. Okay. Importantly, everything depends on theta, the rapidity space, but also on A, if you wish. Okay. Then you can derive this functional equation. This functional equation is a sort of bootstrap equation for this, for people who have worked on this or know about this, for this kernel here. So once you see this kernel, experts are quite used to say, but I can derive something like this, okay? Since you are mathematically very refined, I want again to stress this fact that the reverse is not true, and this is quite crucial, okay? Now, notice that this equation has a sort of two shifts on the right, one shift here. This two shift is new somehow, because there were other examples we were working on in the past, starting from some papers by Zamologikov, and then Roberto, with Francesco, we have developed some, they started actually, I was younger. You can categorize somehow some very beautiful Y system equations using Dingin diagrams. This is, okay, the incidence, this is the Coxeter. So many beautiful structure, but notice that this equation is different from these because you don't have any shift on the right-hand side. It seems a little bit a mathematical observation, maybe it is, but it's quite crucial for physics. Still, it can be seen as a recursion relation in the sense that Pietro is quite comfortable with this. You fix theta, and this is simple recursive equation, okay? For just imagine that is a three-step recursion relation, okay? This is the initial data, and then you have theta minus, theta, and theta plus. A three-term recursive relation, okay? And fortunately, can I go back? Yeah. Here you have almost the same, but you have also these other shifts, so it's a little bit more delicate. For what concerns gauge theories, unfortunately, this A is zero, okay? What is the application of this object, more in general, for the gauge theory? I'll take the question since Jean-Emile somehow asked, although it was a little bit preterintentional by him, I'm afraid, but anyhow, is zero. So the problem will be to interpret this equation more in general, okay? This is an equation that you, due to the your formation, Pietro know very well, you will see in a moment. But I didn't suspect so easily. A crucial point for the physics, but I don't have time, but who is interested, is that these equations are periodic in theta. Okay, this is a very important part, cluster algebra of this story, but yeah, we don't have time. These equations are periodic, this object here is not. Physically, periodicity is attached, for people who know, to the deformation, to the conformal weight of the deforming operator with respect to the conformal field theory. So it gives you a precise information on the infrared, okay? So here we are, there is no periodicity. So there are very big advantages of wave system. Many of you know about this because they notice that from the old approach to integrability, say old, not because because it's the most important somehow, it's not due to me, and we approached Y systems, okay? This is the only path we are keeping, which is Proficius approach to gauge theory. There are many advantages. In all senses, gauge for gauge also we will see for some ODE or OPER construction. But a disadvantage is that, or advantage is that it's not unique, the solution of the Y system. Instead of the TBA it is. It depends on, it can be fixed by the asymptotics, okay, theta going to plus minus infinity. This is a pro because in this way the Y system takes into account for all the spectrum. The TBA was only for the vacuum, for the ground state. The Y system is for all the spectrum. This is the common belief. Still, it has no big proof. What we were discussing this morning will be a way to prove it. Okay, it's ubiquitous, as you know, and sure. Absolutely yes. Different asymptotic means different state. We will see in a moment. Sometimes, I'll show you, this is a little bit here, but as per no, and sometimes it is not considered, different asymptotic of the same Y system may mean also different theory. We'll see in a moment. But the two theories are very much connected, okay? So you have, so it's a very universal object. You know this loop, I can move this arrow. That's a good question, as also the other one. You know it looking at reconstructing the solution and looking at, you can construct the asymptotics tells you about, roughly speaking, the Bethe-Young asymptotic solution. At the beginning, I told you, say this way, yeah, that could be an understandable answer, because it's a technical fact, a little bit technical, but basically, the asymptotics tells you about the large R behavior of your solution. So the asymptotic in itself is somehow the driving term of TBA. Only, let's do this way, I'll write something, although it's still some time. So, this is the ground state. Then if you if you go to an excited state, theta plus infinity is just, for instance, e to the theta, okay? You have this object here, okay, plus, say, schematically, this SI, these are the asymptotic Bethe roots. Okay, this is a precise answer. Why it's a little, it's not complicated. These are, you will see in a moment, these are zero modes technically. These can be computed using the scattering matrix and making these Bethe ansatz. The Bethe ansatz better this way, okay? That's the idea, yeah. And these are called technically asymptotic beta roots or young beta roots. To mean this asymptotic. So the driving terms, but that's as if you think carefully. This is the driving term, and then you have the convolution term. Okay, the convolution terms tells you really what are called technically wrapping correction. I don't know if you ever, probably you heard about this because at a certain moment, okay. Wrapping correction means the Lucier correction, the exponentially suppressed actually MR. Lucier means it's this object e to the MR. MR because it's depressed when R is big. So it's analytical, completed, but take into account by the nonlinear integral. Okay. And okay. It's interesting, but quite mysterious, so understandable, but so it's the Y system is the only functional equation, basically the only, which is invertible, we will see in a moment, into a nonlinear integral equation, the TBA equations. Okay, actually the TBA equations because are the equation for this object, okay, but also for this for the excited states. Okay, so in this sense, the Y system is even more important. A crucial point we have worked on is if there is any simple way to reproduce it, to reproduce the Y system in some way. We will see a way. The general theory is something I left as an appendix for interested people after the talk. We developed a systematic way to construct from simple objects very many Y systems. This is an evolution of the original ODE IM correspondence. So ODE is ODE. IM stands for integral models, but in the old days, when we worked on this, it was just an accident. For some potential, we discovered that there are associated minimal models. It seems to be a sort of magic trick. The general idea we developed in this paper, I will not talking about, is that if you think that the Y system can be generated by a QQ relation, the usual unitarity relation of quantum mechanics is somehow a QQ relation, okay? We will see in a moment what a QQ relation is. And then from here, you can develop a systematic way, given a quantum integrable system, to find some ODEs associated to this. But now we will be instead, quite concretely, to give a further motivation for integrability using gauge theories. And this, in this game, is quite crucial, the ODE correspondence. ODE, I already said, is an ordinary differential equation. EM stands for integral model, although for the moment, for the time being, these will be conformal theories, okay? This is the point where integrability meets somehow Cyber-Witten, okay? Let's see in the simplest possible example. So, as you well know, so the original idea of Cyber-Witten was to reconstruct the prepotential using the two periods, okay, and of a differential. Then you can quantize it somehow using the Krasow-Shadashvili scheme. So in the end, you have an ODE instead of a differential, or if you wish, this ODE is a limit actually of the AGT correspondence, the semi-classical limit, no? Of the and it is the null vector arises from the null vector equation, this ODE. In the simplest case of pure SU2 theory, you have the Mathieu equation, okay, as you well know, and so the quantum, you can imagine that the quantum Cyber-Witten differential is the quantum momentum of the quantum mechanics of this Schrödinger equation, and everything, of course, can be generalized to more complicated theory, but staying simple, the Floquet exponent is the fundamental period. The dual one is this other integration, okay, on P. On this equation has been developed taking back from seminal paper by Bender, Wu, and so on, what is called, and people here are more expert than me, the exact WKB method or theory, and then somehow say that this WKB can be, exact WKB can be imagined to be solved by some TBA equations, but everything has been done not for this case, but for the, if you wish, for the original case of the original minimal models, so polynomial potentials. Doesn't appear in a polynomial. And fascinating, in a fascinated way, this Mathieu equation has been dealt with in a very beautiful paper by Pietro and Jürgen Teschner. Okay, our approach will be still different, but you can make contact with this other works, because we will dealing with functional equations and integral equations. First of all, we go to the sort of, how to say, integrability variables, which are just, you see, from Z we go to Y, we define this, which is called very likely generalized Mathieu equation with the Koch potential, which is a confining potential. More interesting from the intuitive from the point of view of physics. And then we have also this way to parameterize in a different way two independent moduli variables. Theta is a rapidity for us, and p squared is, the Coulomb branch, if you want, basically, okay? Lambda is the width and lambda, okay? But this is the way in which in integrability is this equation. And the idea is that can we use this equation to describe, to get to the Y system, okay? A different approach to the scattering theory. So forget about scattering theory. Can we go from here to there? There were signals. First of all, what we have done is we have generalized this equation, and this is what another open question. What happens? The equation before was the equation for B equal 1. We have this kind of generalization we have done using the fact that this has in common with the previous equation two irregular singularities, okay, if you wish at plus infinity minus infinity, and B equal 1 reproduces exactly the equation, and still you have these symmetries, these discrete symmetries of this equation, which are in common with the Mathieu equation, okay? And we use as a starting point this more general equation, because basically what in our modern formulation of the EM needs are just these discrete symmetries, once these discrete symmetries are broken, and this is the case. So this means are broken in the sense that okay, for instance, you have for instance, actually, this is quite the relevant case. We use as a basis of the ODE-IM correspondence, we use these two functions, the one decreasing at minus infinity and the other decreasing at plus infinity, okay? We have this basis. We define uniquely this basis. The prefactor is arbitrary, of course, but this behavior is dictated, this irregular behavior is dictated by the equation, okay? Decaying at minus infinity and plus infinity. Then what happens is that you have some rotation of the U0 due to the lambdas. And remember that the lambdas are given by this symmetry here, the omega by this other symmetry, okay, which are the symmetries of the equation. But they rotate the U0, the lambda, and the omega rotate the V0, okay? Instead, the other way around, they keep the vacuum, say, invariant, okay? This is what the open question I put forward. I have an interpretation for, actually, I have an interpretation of not only the equation as quantum differential, but specific quantities of integrability in terms of specific quantities of gauge theory, but for only b equal 1. What it is for b differ from 1 is one of the open questions. But since I do have an interpretation for Nekrasov-Shadashvili, we can discuss about it, okay? So be still attentive, but also patient. Also, if I can move the slide, it's not bad. So let's go to the interpretation of the theory. The point of view of integrability, you construct this Wronskian, okay, of the two fundamental, okay, and thanks to the symmetries, okay, perturbative analysis. And then with the omega, you act on this. Remember that the omega rotates to the V1, and you get on the right-hand side this, okay? Very quickly, but this is the way in which you find this relation. This equation is very crucial because it is a relation for Q, as introduced as a Wronskian or the EM, but many of you who are expert more than me in monodromy, Q is the connection coefficient, basically because it's the Wronskian of the two solutions plus and minus infinity on the same Stokes sector. In a Y, we will see that actually there is a simple way to introduce the Stokes coefficient, which is the T, and it's computed in terms of connection coefficients, okay? The T describes the Stokes monodromy, changing the Stokes sector by 2. You see, V1, V minus 1. 2, not confining Stokes sector, as you well know. But going back to this object, so everything about the monodromy is described by this object here, for integrability, for mathematical theory, for monodromy. This is the crucial object, although not gauge invariant. So in fact, I put or Y, because Y will be the gauge invariant coordinate, the geometrical coordinate instead of T, okay, the Stokes coefficient, as you well know. But crucially, you can derive the basic relation, function relation, the QQ system, taking the Wronskian of these two and on the right-hand side, and you get this equation. Okay, this is the so-called QQ system. Okay, do with this. So let's stay there. Originally, the Q function was introduced, not in this context, a little bit different, as a matrix, okay? Many of you know formality Bethe ansatz. In quantum field theory, you can define it. In some cases, it's very complicated. There are a lot of axiomatic field theory to be taken, only conformal field theory. So, it's, as an operator, Q is a complicated object, but here instead we are working with eigenvalues. So scalar things, and these are simple. Somehow, this is the only object you should know, okay? You can imagine what is the question now about this QQ system derived from a very simple ODE, okay? Everything can be generalized, of course. I made for you the simplest example, but concrete, you can do the calculation, It's not if you were a little bit more convinced, you could do the calculation during my talk. And it's important because from integrability, if you expand in theta, you get all the local charges. You know, remember the old definition, the conserved charges, and also the non-local when they do exist, okay? Which is another complicated story. Actually, there is one of the way system. Why? Because then you can think without knowing so much, and this is why it was introduced a lot before, I think also of other papers by Fogg, Gancharoff, and so on. So it was not even clear in the integrability realm that this was a gauge invariant quantity, this y, but you can just play a little bit with your physical intuition. If you define y in this way, as a product of Q, you see that the Y satisfies, thanks to the QQ system, this simple relation. We have already, go. A is connected to B. B, I introduce, I'll show you. Where did I introduce? Let's see. No, you are perfectly right, but P was Q over B, if I'm not wrong. Where is A? Is it defined? 1 and 2P. Okay, 1, okay. No, this is an honest question, because I encourage you to and P, we have to go a little bit back. Okay, and P is B over Q, and Q B plus 1 over B. Okay? But this is relevant because you notice that this is helpful. This is not just because of your question. I could P equal 1 symmetry. B? Absolutely, yes. B equal 1 is exactly the gauge theory. Okay? If you want to add chiral matter, I know you have B1 of mass is 0. So can be an integer, not an integer. Apart from these 2 points, we know very little about general B for gauge theory. But the Stokes sector, as Pietro and many others maybe can teach me, not you maybe, the Stokes sector of this equation is complicated than integer B. It's more complicated than B equal 1. Then integer B is more complicated, and the general B is even more complicated. But B equal 1 over square root of 2 is chiral and F equal to gauge theory. So thanks for the question. Now, so you know, but you know, sorry, I'm taking, I'm quite long. So, but this is exactly, I should rush. Someone wants to say, I'll happy to finish. Anyhow, and this is the same. We are quite happy. The point is that since we are quite evolute now, we know that, okay, this is the same looking equation, but the solution is the same. That's a different story. Okay, and now the main trick comes into the game. We have to invert taking the log of this equation. We have to invert this equation. You see, there is a shift here. We have to invert basically the shift operator. Okay? And the inverse of the shift operator is basically 1 over Cauchy. Okay, we can do it. But the point is that this object here has 0 modes, object that makes 0 when you act using S minus 1. Okay? Okay. And these zeros do appear as a driving term. Okay? The generalized Mathieu equation, so for B, for generic B, I'm working with generic B now, so in general, produces only one y, no? Because you have a differential equation. You compute, in theory, you can compute q, and then you can compute y or epsilon, okay? And for large theta, you have one specific behavior, okay? For large theta, you have e to the theta. Ah, that's good. For theta going to plus infinity, that's okay. It's a relativistic particle. Unfortunately, from the differential equation, you get that from theta making some WKB analysis going to minus infinity, epsilon is a constant. I'm cheating a little bit, but is for sure not e to the minus theta, something which is exploding. And this is bad, because this means that this theory is not Sine-Gordon equation. It's something different, okay? You may think, I'm lost. No, you are not, because you understand on the physical ground, and people working experts on integrability already know this, that if you take this relation but send m to 0, you keep this relation for large theta, but somehow only for large theta. This is called technically the kink limit in TBA, it's very well known, and you are left with this behavior, sending m to 0. But we can send, and we know what happens to hyperbolic Sine-Gordon is to 0. You know that, no? Liouville field theory. Liouville field theory. And Liouville field theory. You are in a clever way going to the conformal point. No C equal 1, we can discuss about no C equal 1, but this is obvious why not from the point of view of TBA. And you get this exact TBA, you extract the exact behavior at large theta from the ODE, and you get this exact equation, which is exactly Liouville field theory. Then, as said, thanks to the fact that you don't have this, but you have only this, which are called kink equation, you can compute exactly the central charge. Confirm you that this is the TBA and for Liouville field theory. So, what we discovered, making contact, is that Liouville field theory, which is nothing to do with AGT, is another Liouville, unfortunately, or fortunately, at B equal 1, only B equal 1, interpreted as quantum Seiberg-Witten theory, Nekrasov-Shadashvili, okay? In specific, we also found full correspondence because we found that the T is by cosine of the Floquet, so the gauge period A, and Q is the dual period. We also found that Y is basically in that case, if you elaborate a little bit, at B equal 1, Y is Q squared because A equals 0. And so you don't have shift. And so it's basically the squared. And so from the QQ system, basically do coincide with the Y system in the particular case. And you can derive some gauge TBA equations. And you, who are experts, recognize immediately the strong coupling spectrum of the theory. So this is the strong coupling. Weak coupling is a different story. But from my perspective, I have other ways to get to the weak coupling. So I don't have so much, very likely. How can I go, or I stop? Sorry. 5 minutes is okay? Okay, I'll try to finish in 5 minutes. What I can, since I identified the period, I can find also a different I can identify where the derivative of the potential with respect to A, okay, the dual period. In which way I use the ODEM basis. I can connect the ODEM basis to the Floquet basis. This is the Floquet solutions. They have this as a period, the A as a period. And if I consider this one of the two Floquet, the normalization doesn't matter of the Floquet, the one with Floquet index plus A, okay, and I noticed that I'll show better in a minute how it works. It acquires a phase going to from minus infinity to plus infinities. Okay, this phase is exactly AD. Okay, I'll show you in a moment. And this is somehow an ODE in instant-on correspondence. The details are following. And Q can be written in this way. Okay? Because of this mapping between the solutions of the ODE and the Floquet. It takes some calculations, but in the end, you can write Q in this way. Alternatively, just to give you an explanation, this is the general solution of the QQ system, okay? Provided AD verifies this simple sort of quasi periodicity equation. So once shifted by I pi over 2, it changes by A. And then what is left is that you have to check the theta going to plus minus infinity to identify that this AD satisfies the one derived from the prepotential, verifies this equation. And in addition, it also has the right asymptotics for Q. This is another way to derive this simple looking formula here. And Q equals 0 are the beta roots, but also are the quantization conditions, which are also interesting for. So a little bit more in details, this is what happens. These are the Floquet solutions. At minus infinity, it goes this way, okay, with a constant. You fix this constant. And then you see that solution, how it behaves at plus infinity. The same behavior, except y goes into minus y because of parity. The same concept, but it acquires a phase. This phase can be proved, thanks to this property, many ways, to be exactly AD. Okay, so AD is hidden somehow in the asymptotics of the Floquet solutions. Okay, there are some comments. So this is the weak coupling somehow. The weak coupling is somehow you can elaborate TBA, will be infinite dimensional, but more easily, I think, you can write down the TQ system for the self-dual Liouville theory. So Liouville theory, but B equal 1, which is even simpler. This relation will be in general, but we don't know how to interpret it for general B. For B equal 1, gives us information about the weak coupling. So, and then these are quantization of the Liouville. The simplest case, this is not the black hole, is a sort of black brain. So exactly the same equation. And we notice that also using zero, nothing but changing variables, the black holes asymptotic relations. And then you can generalize it, and interesting, you have this extremal Kerr black holes, Reisner Nostrum for different values of the flavors. You get Schwarzschild for an F equal 3. Okay, and okay, this is why the quasi-normal modes are zeros of the Q, okay, and the Q satisfies, in B equal 1 is this simple relation. It's a sort of up to quadratus. And these are also strong implications for gravitational physics, because this is the spectral determinant, and so since there is a partial a PDA at first order and also higher orders in perturbation theory, you have more than the quasi-normal mode, than the zero. You have really the spectral determinant of the ODE and some information about the PDE that can be developed and log numbers and for gravitational waves, interesting for gravitational waves physics. So very quickly, there is another more complicated way to see the appearance of this Mathieu equation. For people interested, we can go further. The idea is that there is a, you remember the parent theory, no? The parent theory is quantum Saint-Gordon. You can write down quantum Saint-Gordon. Basically, this goes back to GMN, but also subsequent papers. Using so somehow doing some ODEM for the massive case, which is a lot more complicated, but you can do this. So far, we have done only massless cases. So you have to start with some zero curvature condition, so 2 lakhs for the quantum Saint-Gordon, classical quantum Saint-Gordon. Okay, and you have a way, so you have 2 lakhs operators, 2 Schrödinger equations, somehow when you reduce from first order differential operator to second order. And in this way, you get the massive theory, which is exactly quantum Saint-Gordon. You have also the possibility to add moduli. If you don't add moduli except the energy, you have to add, you have a TQ relation, which is now massive. It's the parent TQ relation, okay? Floquet solutions for this equation. They are quasi-periodic in this way, exactly. Okay, I jumped this, sorry. And when n goes to infinity, I land on the child theory, okay? Because this equation becomes a differential equation. You can see this in 2 ways. One is the very straightforward calculation. You compute t. It's not so simple, but you can do. And this is related with your paper, with your work, Pietro. This is even more complicated. Or a little bit more clever, is my idea. We computed it in this way. Everybody knows that you take Saint-Gordon equation, you make it radially symmetric, you land on the Painlevé third 3 equation. Okay, this is simple, 1-line calculation. But something that I didn't find in the literature, but we did, it's not so complicated. You do the same limit on the lax operators defining the Saint-Gordon equation. This is a little bit more relevant. Then you have 2 operators, one t and one in y, Saint-Gordon. Where do they go? They go to Painlevé third 3 lax operators, okay? Then, which is another piece of novelty we have discovered, okay, but you say, okay, but this is not Mathieu. You are almost right. If you go to the pole or the 0 of the Saint-Gordon equation, in ODEM it appears quite natural. I could explain why. On the pole, the first pole, the nearest pole to the origin, t equals r, is the 0 of the pole. This is the child rapidity. Then you get exactly the Mathieu equation from this first lax equation. This is another way to get the Mathieu equation from Painlevé theory. And then there are conclusion and perspective, but okay, anyhow, I think I finished. Thank you. Thank you very much indeed. Thank you for your patience. No, no, because they are massive. And I think Pietro can answer this question better than me, but I think that they are dealing with compactified theories. So in any case, it's the TBA. So they have this driving term. They don't have, my TBA is a lot simpler. I think the physical, this is due to, oh, sorry. This is due to the fact that they are working with theories, if I remember well, which have four dimensions, one is compactified. And I never fully understood this point, but due to this fact, I think they got they basically get the TBA, which is from the integrability point of view, although they don't write it, I don't know why, it's a very well known quantum single. They have basically these lax operators. And so you have Saint Gordon, you have some certain number of moduli in this way, going from Z to W using this polynomial. The moduli are this C here. Okay, at the conformal point, you will get to polynomial potentials. Okay, analyzed by these people. But anyhow, these are the potential of the original ODE-IM. They are massive. And then there is this paper by Luciano Fenzamologi with 0 moduli, except C0, so the energy. And then we found, you can have a look at our paper in which we developed the full structures of their TBA. Also, about TBA, if you remember the paper well, when they published the paper, they wrote these equations, and then there is a note added, thanks to Zamologico, we noticed that, and they quote also the wrong paper by the other Zamologico, because the quote, and this makes a lot of confusion, because they quote the paper on ADE TBA, but this is not ADE, it's homogeneous Saint Gordon, which is fully different from ADE. Yeah. For my TBA. So for the, yeah? Yes, of course, we did. It's this paper by myself and Marco Rossi. Yeah, sure. No. It's the reverse. So this means that the seminar was a failure. No, it's the reverse. You derive Q, and then derive Y, and then, if you wish, their TBA, which is not there. It's a TBA derived 20 years before by Fring, Miramontes, and so on and so forth. You find the quotations here, which is homogeneous Saint Gordon, which is a very complicated model, is basically Saint Gordon with infinite masses, mass scaling. You have a sub-theory, which is the one they analyzed and we analyzed using ODEM, okay? But our perspective is more complicated than we developed here, will be here, this object here. You write down these lax operators, study the ODE-IM correspondence for these operators, which is not what they did. They did only the TBA. You derive the Q, traditionally, from looking at the monodromies. From the Q, you derive the TQ, the TT, and from the TT, you have the T. There is a full structure. We analyze the full integrability structure of their lax operators. Their lax operators are the classical lax operators of homogeneous Saint Gordon, of some subclass of homogeneous Saint Gordon, yes. And you can derive more than the TBA, yes, starting from the differential operators, which are, if you allow me, are two opers, although they are not opers, okay, because there are two lax operators, you study the monodromies, as we have done here for the child theory. This is the parent theory. We did it in this paper with Marco, which goes back by some years, and you derive the Q, the TQ. When I say Q, it means the QQ system, the TQ, the TT relation, and then we wrote down the Y system, and from the Y system you invert to the TBA. And you get the TBA. Also because in this way you can derive also excited states, because they work only with, this is what they wrote as integral equations are valid only for ground state of homogeneous Saint Gordon. For sure. If I don't die, I'm here. Thank you, actually. I beg your pardon. I was quite long.